So anyway, thanks to Brett, I now have over expectations. So everybody calm those down a little bit. So I want to talk about adaptive trials and trial simulations, and I'm going to pick on Sam at the beginning. So I'm not allowed to. So anyway, I got a very nice email earlier in the summer, which I summarized as "Don't be so inspiring." So anyway, while I'm talking about adaptive trials and trial simulation, one thing to keep in mind, most of you are in this situation, you're doing trials for the first time or one of the first times. You have a lot of things that you have to deal with in terms of setting up pipelines, making sure patient data is entered, making sure that you've gone through IRBs, making sure that you've done all of the other things just to make the trains go at all you're dealing with at the moment. What I'm talking about today with adaptive designs, these are trials that would require interim analyses, and they require work to go on, and effectively all the trains that you have to make run right now, they have to be running optimally in order to make the adaptive designs work. So in a lot of cases, these are not appropriate for your first couple trials. Our hope by giving you this talk is that you kind of see that, once you've got this infrastructure in place, you can do a lot with it. And so as you go further, you can consider these kinds of designs. I'm going to start with adaptive trials. I'm going to talk about that for a little while, and then I'm going to talk about simulation, which is how we usually evaluate them. So anyway, I am a private consultant. That means I have multiple clients. On the other hand, hopefully I know what I'm talking about. So if you have adaptive trial design, we always make choices at the beginning of every trial. You have to make choices. What doses do I put in the study? What patients am I going to enroll? What's my sample size on the basis of the treatment effect? A lot of times we have to make guesses at that. We don't know what they are. Those guesses have big implications. If we pick wrong, if you say, I want to use control, and I'm going to use this dose of the treatment, well, if that dose is too high or too low, that can cause trouble. So a lot of times people come into trials and they go, well, maybe can I figure out that information as I go through the trial? I really don't know. I don't want to pick a sample size. You saw this in Stryker Dawn in the keynote. I don't want to pick a sample size of 500 when the answer is going to be no at 200. I don't want to pick a sample size of 200 if it actually takes 500 subjects. So I don't want to end up on either one of those extremes. Can I just do a trial that can go either way? Can it do 200 or 500, depending on what's most appropriate? So adaptive designs are aimed to do exactly that. Somebody asked at the keynote, why didn't you just run a phase 2 and then a phase 3? Why did you do this kind of adaptive design? And it's a very reasonable question. One way to think about all kinds of drug development is that they're always adaptive. But what tends to happen? We run a trial, we focus on making sure the trial runs, we get the data, and at that point we stop. And we make some decisions. And then we go and run another trial, and we kind of bunker down and get all the data, and then we stop, and then we open everything up, and then we make some more decisions, then we run another trial, and we do that. So you can kind of think of that as if you were driving a car. I'm going to get to an intersection, I'm going to point the car in the right direction, I'm going to close my eyes, and I'm just going to hope for the best, I'm going to hit the gas, and as soon as somebody honks at me, I'm going to stop, and then I'm going to open my eyes, I'm going to see where I'm going, I'm going to turn the car, and then I'm going to close my eyes again, I'm going to drive the next intersection. So this is essentially what standard drug development does. Usually if you're driving a car, how many of you keep your eyes open when you're driving? All right, there's very few people who answer that. All right, so anyway, adaptive designs, to be honest, we don't have our eyes open all the time, but we like to claim we do. In reality, what we try to do is we close our eyes for a little while, and then we open them, then we close our eyes for a little while, and then we open them, and so on and so forth. But we try to open them more often. And decisions that we can make mid-trial, we like to go ahead and do. The kinds of information that you can react to. The most basic idea. Suppose the drug doesn't work. You can get partway through the trial. This can't possibly, it's not doing anything good. I'm going to enroll like a 1,000-patient trial. I'm 400 patients in, there's no effect whatsoever. This is not going to have a good outcome. You can enroll the other 600 patients, but this is not going to end up with a successful trial. There's reasons to declare futility. You can also get information if you're doing a dose-finding trial. You start off, you've got 4 different treatment arms in your study. You can find out halfway through, I don't know which arm is best, but I know that arm is bad, or I know those 2 arms are bad. It makes sense to go ahead and get rid of those for a couple reasons. One, if it doesn't work, there's no reason to give it to patients. And the other issue is, if I've got 4 treatments and those 2 don't work, if I'm deciding between these other 2, the more patients I can put on those, the better chance I have to figure out whether the 2 survivors, which one of those is actually best. So we can make those kind of decisions. We can also do things like if there's a group of patients that is not benefiting. So one of the things in Stryker Dawn was about how long, size of the penumbra, all of this stuff. Are there certain kinds of patients who benefit and certain kinds of patients who don't? If you can detect that in the middle of the trial, you can change your enrollment criteria as you go. It's usually called enrichment. And all of these things are designed to try to make the trial more efficient. In effect, the summary here is when you run a clinical trial, you're usually trying to answer more than one question at the same time. Ideally, you would like to. And some of those questions get answered before others. If you walk in, I've got 3 questions that I want to answer, I'm expending resources on all of them. If I've answered the first 2, let's stop trying to re-answer the first 2 and focus our resources on question number 3. All right, let's see, talk about that. Okay, so different kinds of adaptations. We talked about futility stopping, so that's just stopping the trial because things aren't working. You can stop the trial because things are going well. So it looks like I have a tremendous effect. Now, admittedly, this doesn't happen as often as we would like, but it certainly is possible. If things are going well, let's move on. Let's get the treatment to the patients. Or let's go to the next trial or whatever the appropriate thing is. You can add or drop arms. So you could come into a study, you've got 5 doses. As I said, some of them are doing badly. You can push them down. You can do that in reverse. If you wanted to start a study, a lot of times we do something called a top-down design. You come in, you start with a control arm and a high dose of a drug. If the high dose looks like it's doing well, that's good. You may have some sign of efficacy. But maybe there's side effects of this. Then maybe you want to open up arms. So you want to actually open up, half the top dose or 3/4 of the top dose. You can absolutely do that. I'm going to talk about an example of adaptive randomization. This is a situation where you change the randomization ratio as you go to try to allocate more subjects to treatments that are doing well and less subjects to treatments that are doing poorly. I'll save that for the example. And then enrichment, which is a situation where you're changing your patient population as you go. And you can do that. You can start with something broad and restricted, or you can start with something restrictive and go broader. So you may say, okay, I want to look at stroke patients that are 0 to 6 hours, and if both are doing well, I'll expand and I'll start including 6 to 12, for example. All right, so let's see. So here's an example. So this trial, we designed this for the Gates Foundation during the Ebola outbreak. We had multiple drugs that, lots and lots of things people were willing to try for Ebola. I'm going to simplify this a little bit, but not that much, and talk about 4 possible treatments, A, B, C, and D, not giving any names. To be honest, we didn't know all the drugs that were coming into the trial. So they had a separate group going, they were a drug screening committee, and we were told, write the protocol and we'll tell you what the drugs are later. And this works. They also, combinations of these drugs were allowed. So you've got A, B, C, and D, but you can also get A plus B, A plus C, A plus D. I'm going to, for the purposes of the example, I'm going to allow any combination of 2. there were some restrictions. You know, you can't give these two drugs together. I'm ignoring restrictions. We had some restrictions on what we could do with kids and what we could do with pregnant women. So anyway, we had to deal with all those kind of issues. I'm ignoring those complexities at the moment. All right, so I've got 4 treatments, and I want to consider combinations. So that's 10 things. 4 singles and 6 combos that I could potentially do. So how do I go through that space? I'm going to have, I don't have to put it up yet, but I've got 250 patients. I can pick one and test it. I don't know how many subjects to test it at, so I can say I'm going to start with treatment A. And I'm going to run that until I'm done. I don't know what done means exactly. And if it doesn't work, I'm going to go on to B. If it doesn't work, I'm going to go to C and so on. And then I'm going to go to A plus B. I can work my way through. That is a fantastic strategy if you can pick the most likely treatment that's going to work and test that first. Now, of course, what typically happens, you put enough people in the room, there are 10 combinations. People will tell you there are about 11 or 12 things you should try first. And generally speaking, it's hard to guess what the first thing is. So this strategy requires very much that you actually know what's likely to work and what's not, which is, in this case, wasn't viewed as feasible. The alternative strategy is to try to look at everything at once. Well, we have 250 patients, so there are 10 different combinations here. If we do everything at once, we're going to end up with 25 patients per treatment, which isn't enough to do a lot of good inferences. So that presents a problem too. We end up with essentially 10 separate trials, all of them being underpowered. So that's not fun either. So is there any way to kind of bridge the gap between these? So here's what we did. We did what's called adaptive randomization. And in this context, what that means is we start with subjects on every single treatment. So we gave some patients A only, B only, C only, D only, A plus C. Everybody got some of the combinations. We looked at the mortality rates every few subjects. So as the data came in, there are interim analyses. So every few patients we go, we look which treatments are doing well and which treatments are doing poorly. And we adjust the randomization. So and we did this on the basis of a generalized linear model, which you may or may not have heard of. But anyway, if drug D, so you can get drug D in multiple ways. You can get D alone, A plus D, B plus D, C plus D. So we fit a model that if D looked like it was doing well, more patients got D, and the model had abilities, if D and C together are doing particularly well, then you would have more of a likelihood of getting to that combination. Skipping the details of the model. But essentially, we're trying to adjust every time. Now, when you do this, you definitely want a statistician to do this with you. There are risks to this. You don't want to adjust too early. Hey, you've got 5 patients and that treatment's looking good and that treatment's looking poorly. Let's immediately enroll all our patients on the one good one, because you can overreact to early data. So you have to know how to design this and get some help so you don't overreact to early things. You use the information, but you don't overuse the information. And we know how to do that. All right. So as we do this, I have to keep track of, well, does this method work? And so we kept track of a couple aspects of this study. You can think of this Ebola outbreak. We wanted to help 2 groups of people. We wanted to help the people in the trial. So we wanted to make sure that the people, if you walked into the Ebola clinic that was doing this, that you were more likely to get good treatment and use the information. So the patients, as they come in, every patient is helping the next patient be more likely to live. We also have the notion that we want to pick the right treatment at the end of the trial. So this treatment might be used generally when we're done. So we want to get it right, because that allows us to help external patients outside. So we're going to try to maximize both of these. 250 patients, so some details. Let me make sure I got all this. Keep in mind that this trial is set for 250, but in theory it was also, there was an option to run these kind of trials perpetually. So this trial has some built-in notion that we might even keep going beyond that. All right, so good. Pull this up. Let me start on this scenario. All right, there's lots of stuff on this slide. So this is intended to get an idea of how well does this particular design work. The blue numbers, this is a hypothetical scenario on how well each of these combinations work. So you can see the death rate on drug A alone, so this is A crossed with A, that's A alone, is 40%. Drug B, no matter what you do, drug B alone or B with A, that's also 40%. You can see these combinations. So this is C, and then C with A or B, they're at a 30% death rate, so we're getting some help. Where you want to be here is if you get C and D together, that's this one, the death rate drops from 40% down to 10. So that's definitely where we want to be. And then if you get other versions of D, the death rate is 20%. So certain places are better than others, and C plus D is the best. What this trial is doing is we start off, we enroll, we look, we adjust randomizations, we enroll more, we look, we adjust randomizations, we do that over and over again. So where do the patients actually end up? The numbers on the top, these are the number of patients that, the average number that we put in each cell out of the 250 patients. So A alone, on average, only got 6 patients. That's a high death rate. We got away from it very, very fast. These, you can see 8.2, 6.1. These are a little bit better. They got about 15. This ideal combination, this got 90 patients. And if you take the drug D has 190 patients on average out of it. Now some of those are at 10% and some of those are at 20%, but they're all, we've cut the death rate in half on D no matter how we do it. We pushed more patients onto those arms. So this has been beneficial to patients in the study. The other aspect of this, and I know these numbers are too small, if this number's at the bottom, these are giving the power of the trial. What are the odds that this trial, at the end of the day, comes back and says, I think C plus D is the best option? If you do this design, the probability of that is 89%. So something close to, if you want to call that akin to power, you've got a good chance of picking the right dose. If you don't pick C plus D, you're going to pick D plus something, virtually guaranteed. A trial that if we had run 25 on each arm, it does fairly well as well, but it only has an 81% chance of coming back and saying C plus D. So not only are we benefiting patients in the trial, we're also benefiting patients outside the trial by being more likely to give the right answer at the end of the day. I've got some other scenarios, so I think the slides will be publicly available. I just have different versions of different kinds of scenarios, which drug combinations might be best, and just to illustrate some consistency over how well this works. So this kind of trial, this is now sitting on the shelf in a lot of outbreak scenarios. So if there's an endeavor called PREPARE in Europe. And so if there's ever a flu outbreak in Europe, there is a trial sitting on the shelf somewhere that is ready to be grabbed out, and it doesn't have any drug names in it either. So, and people, this is what we ought to do. One of the difficulties in this trial never got run. And so I should definitely emphasize that. This trial was about to be run. The joke at Barry was that as soon as Ebola saw it coming, it went away. So it was interesting. So we actually sat and watched the outbreak numbers, And, you know, we could see, you know, we finally hit the dwindling. We knew it was never going to go. But it was about to. So it was interesting. We had gone through all the efforts of, we had dealt with West African IRBs and all the clinics. So it was all set up to go. But it never went. All right. Okay, so I'm switching gears a little bit. So how do we assess such a trial? So I've got this adaptive design. If you're designing what I'll call a standard trial, so Sharon, where's Sharon? So did you show your cartoon with the two little blobs?
It was in the slides, but I can't remember if we can make it run.
Okay.
Yeah.
So anyway, you know, if you go to your statistician, I have this effect size, I want to run a 2-arm trial, just tell me what the sample size is. Well, you can do a calculation for that. You can plug it into a formula and it will tell you need 500 subjects. The kind of design I just showed you for Ebola, where we're going to run interim analyses every 20 patients, and we're going to change the adaptive randomization, and we're going to run it to the end. In theory, there are probably formulas for that. I have no idea what they are. I don't think anyone has any idea what they are. So we can't just plug in, we can't pull out a little chart and go, 10 interims every 20 patients, adaptive randomization, generalized linear model, 500 patients. It doesn't work that way. So instead what we have to do is we have to turn to simulation. So when you hear a notion of simulation results, I want to kind of demystify that and say, here's what it actually means that we're doing, because we're not doing anything incredibly extravagant. So this is, I'm going to call this a complicated question. I'm not claiming it's really complicated, but I think it gets the idea across. Suppose I want to ask you, I'm going to flip a fair coin 10 times in a row, and I want to know the probability of getting a streak of 4 heads. So, I flip it, I could get heads, tails, heads, tails, heads, tails, heads, tails, heads, tails. There was no streak. I could get heads, 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 tails, heads, tails, whatever I get for the rest of it. That had a streak because I got 4 heads in a row. Anybody have any guesses if I do this? How likely it is you will get 4 heads in a row? I'm flipping a fair coin, 50% heads, tails.
Quite high. Quite high.
Well, quite high? What do you think?
This is the way the probability works. I don't know how to explain it, but it's 6%.
So what's quite high?
Maybe I'm
Over? Statistics means never having to say you're certain. So, over 50?
If these are all independent trials, then obviously it's 1/8, 1/8, right? Probability is 1/8.
Well, you get it, you get it in multiple places. So, all right, think about it right. So, anybody have a different guess?
Less than 6%.
All right, less than 50, yeah.
25%.
How do you get 25%? Google. So I didn't know that I was a college professor before this, and I quit before students like you were in my class. All right, and he's completely wrong. It's 24.5. So anyway, so you can do this by going to Google. You can also do it. I can teach you a little bit about Markov chains and a few matrix manipulations, and you can get this answer. So this is not, this isn't incredibly complicated stuff. I could spend a separate hour lecture and I can teach you how to do this calculation. There's an easier way to do this. I can also sit on a computer and I can just let the computer flip coins. They love this. So they can flip it 10 times in a row and just go, well, did I get a streak of 4 heads or did I not? And I do this over and over and over again. And I can just count. So I have the computer simulate this 100,000 times, flips, a million coins. And it basically goes, how many of them had a streak of 4 in a row and how many didn't? So it's just counting stuff, big bookkeeping problem. And so simulation 1, here's my sequence, that's a no. Simulation 2 is a yes. Simulation 3 is a no. And I just do this over and over and over and over and over again. All right, so I did this. I ran 100,000 simulations, and you can kind of watch this converge. So there's variability here. If I do this only once, I get yes or no. But the more times I do it, the more accurate it's going to be. So at 100,000, I actually got down to 24.5%. If you're doing 100,000 or a billion simulations, you're going to get a very accurate number on how this works. Okay, so let me skip this one in the interest of time. So let's go back to reality. In clinical trial designs, as I said, we usually just use the math. You can also, to my knowledge, there is no Google sample size calculator for adaptive trials. In complex trials, what we have to do is we have to do this simulation. So what we actually do is for the Ebola trial, for example, we had a computer generate subjects. So it walked through the study. And it said, here are the subjects that came in. We flipped a coin. Did each of them live or die based on the probabilities I showed them? We then said, here's what the model would do. Randomize more to these arms, less than those arms. And we walked through every interim analysis and got to the final analysis. What combination did you pick? How many people lived? How many people died? And we went back to the beginning. And we had the computer run another one, and another one, and another one, and another one. And so what you saw in those graphs was just the averages out of thousands upon thousands of trials. So we often use simulation to tune our design. So somebody asked me last night, when you're doing adaptive randomization, how do you know, when you do it, how do you know when it's too early versus too late? And often we run simulations and we just test them. So we run simulations where we do the interim analysis early, we run simulations where we do it late, we run simulations where we do it in the middle, and we take the one that works the best. So this is an example. Let's see how I'm doing on time. Oh, good. All right, so I've got a trial with 2 doses, low and high. I'm going to enroll 216 patients in total, 36 patients a month. I'm going to have my endpoints a composite event. So this is some composite of safety and efficacy. So it's certainly possible that my low dose might be better than my high dose. So I'm going to run a study control, low, and high. My 2 questions are really, does this work? Does low or high work? And my second question is, if it does work, well, is low better or is high better? What I'm trying to figure out. Increases of 2 units are considered valuable here. So here's a simple trial. I can enroll 72 patients per dose. 72 on control, 72 on low, 72 on high. I'm gonna, so Michelle, you happy? I'm adjusting for multiplicities. Okay. So I'm going to test each of them, accounting for the multiplicity of the 2 doses. My trial is always going to enroll 216. So suppose the drug doesn't work. So there's no effect whatsoever. So by effect, I mean difference from control. So no difference for low dose, no difference for high dose. In that case, I've controlled the probability of success 2.3%. This kind of multiplicity control is too conservative. And so essentially, I'm always going to enroll the full trial and fail. That's bad. I'm going to put in a futility analysis in a minute. Suppose the drug does work. So low is 1, treatment effect and high is 3. My power here is 77.1%. So I haven't hit the magic 80, which is of course a line in the sand. But anyway, here's my notion of, am I going to win this trial? All right, so here is a naive adaptive trial. So after 1 month, I'm going to stop the trial if neither dose achieves a 2-unit increase. So I'm just going to give up. So if they're both at 1.9, I'm going to give up. That may not be a good rule. We're actually talking, we're going to test it and see how good a rule it is. After 3 months, what I'm going to do is I'm going to choose the dose with the higher observed mean. And my slide's not good here. I'm going to keep going. So I'm not stopping the trial, but after 3 months, I'm going to drop one of the doses and I'm going to go on to the end. So I'm going to try to get more patients on here. And at the end of the trial, I'm going to perform a t-test with the selected dose. So a standard thing that would happen here, let me just give an example. If this is my data, I come in, month 1, I've got 6.4 for the placebo. The low dose is looking good, the high dose is looking good. I continue. I've got something, they're 2 higher. At the month 3 dose selection, the low dose is doing better than the high one, so I choose the low dose. I continue to enroll the low dose, and here's at the end, I've got 5.2, 7.9. This is a successful trial. P is less than 0.01. It's possible I can get different data. So this would be a situation, I come in, 6.8, no effect on the low, 1 point effect on the high, doesn't meet my 2, I can declare futility. So simple rules. So I can simulate this. I can go through and have the computer generate data, and at month 1 it simulates that I do futility. At month 3 it can just check to see which one's the highest. It says what happens at the end of the trial. So I just do this over and over and over again. So let's focus on 1,000 of these trials. So the graph that you're seeing here, these are the simulated results on the low dose. And first off, look at the variability here. This is pretty big. It's always bigger than you think it's going to be. Some of these are at -7. They're 7 units worse than the control. Some of them are 7 higher than the control. So they're all over the place. A lot of variability. The high dose is got similar kind of variability. This graph's actually symmetric, so I pulled it out. That probably was a mistake in retrospect. It's amazing when you're up here, you realize all the things. So what happens here? I can figure out which ones I would have stopped for futility. So I would have stopped 679. I stopped all the ones where neither dose has a 2-unit increase. So all of the red trials, they're done. That's 679 out of 1,000. So the odds that I will stop for futility is about 68%. That's a good thing. I got out of 68% of my trials when the drug doesn't work. There's a flip side to that. Suppose my drug does work. If it does work, I don't want to declare futility because the drug works. And it turns out in this case, these points, they're shifted a little bit. So remember, when the drug works, the low dose effect averages at 1, but with a lot of variability. The high dose averages at 3, but with a lot of variability. So how many of these do I actually kill? So I kill about 31% of these trials. So that means that I am mistakenly stopping 31% of trials when the drug actually works. That's getting out of a lot of trials that would be otherwise effective. All right, so what do I do? What's the central problem here? One month's too early. I just don't know what's going on at that point. And you can take this graph. I've taken those 2 points. I showed you what happens when the drug didn't work and when it did. I've just overlaid those together. So the kind of variability you would see when the drug doesn't work, that's in purple. And the kind of variability you see when the drug does work, that's in green. Those 2 distributions, they just overlap. There's no way to tell at 1 month, am I from a situation where it works or am I from a situation where it doesn't. I can kind of get some hints at the extremes, but I can't get a really strong trend. So the easiest thing to do is to change the rule a little bit. So if I can't really reliably declare futility at 1 month, and I should be careful, you can have a very stringent rule at 1 month and just try to take out the very extreme bad results. I might be able to do something like that. But another rule is just to take the month 3. So at month 3, I'm going to change my futility rule. And I'm going to change it to something more statistical as well. So I'm going to let neither dose has p less than 0.25. So my new futility rule is now later. If going to take a p-value on low dose, p-value on high dose. If they're both above 0.25, then I'm out. So nothing's heading in the right direction. The nice thing about this, the p-value itself, there's some scaling with the sample size and some accounting for variation. So that's a good change. This is what they look like at 3 months. So notice that the scale of the data has come in a little bit. The last graph went from -6 to +6. Most of the data here is -4 to +4. That may seem a bit minor, but it's actually pretty important that it started to come in. The other thing that's happened, the simulated purple dots and the simulated green dots, they're now separated from each other. There's some overlap. There's always going to be some, but there's a lot less than there was before. So if you look at this, I should get back up. You're going to declare if the drug is actually effective, only 5.6% of the effective drugs are canceled. So out of the 1,000 green dots here, 56 of them are where you kill the trial. So simple estimate. If the drug actually doesn't work, so if you're in the purple dots, 62% are stopped at that point. So I'm not getting rid of good drugs, but I am stopping a fair amount of bad ones. Fair warning, it is impossible to do this perfectly. You will never see a futility analysis where I will get rid of all ineffective drugs and I will never get rid of an effective one. If you were at the point where you could do such a thing, you could just stop your trial anyway because you'll know the answer. You can't, in the middle of the trial, you have incomplete information, so you're not going to make a perfect decision. Your goal is to make sure if I have a chance at winning, I have a chance at a good drug, I don't want to kill it, but I want to get rid of what I can. All right. So here is the other thing that's going on. I need to know about my dose selection. So remember, that was going on in the background too. Am I picking the right dose? I'm not going to worry about it for ineffective drugs. So, because there is no right dose, they're both ineffective. I really just want a futile trial in that case. But in the situation where I have an effective drug, it's important to me that I actually get the right one. So if the high dose is at 3 and the low dose is at 1, I want to pick the high dose most of the time. These same simulations, those same 1,000 points, can tell you how often you're picking the right dose. So these are the 1,000 from the effective trials. What I'm doing is I'm going to pick whichever dose is doing better. That means I pick the high dose on this side of the line, and I pick the low dose on this side of the line. And remember, these are futile at 3-month analysis. This does pretty well. So I pick the low dose 73 times. All of the rest of them, I do 871. So through simulation, I've answered a lot of questions. How many are futile? 56. How many pick the low dose? 73. How many pick the high dose? 871. I've got all those percentages, and I haven't had to do any math. And I haven't looked at Google. What's your name, by the way? What's it? Okay, I'll remember you.
You're being too inspirational.
Am I?
Everybody's going to want to do an adaptive design now.
Okay, yeah, no one should do this. Anyway. Okay, so let's see. What have I gained for this? So my total results. If I talk about ineffective drugs, where I've got true effects of 0 and 0, I have had futilities 626 times out of 1,000. I've gotten low dose picked and win 11 times, and the high dose picked and win 9 times. So you can think of how's this trial going to win. It can stop at 3 months or go to the end, and then if it goes to the end, did I get a success or a failure? So that's what this table is giving us. So most of the time for ineffective drugs, we just stop at the futility analysis. And if we continue, we get a few successes and mostly failures at the end of the trial. This is the one that we care more about. We've screened out, so this is the effective drugs, we've screened out 56 failures here at the interim. But we've also, of all the trials that continued, a small fraction picked the low dose, the large majority picked the high dose correctly, and most of those went on to be successful, 795. So what has happened is, if you take my power, I've also got some low dose wins here. It's a little hard to figure out how to interpret these, but the power of my trial is 82%, because that's all of my wins. So let's get a comparison here between the fixed and adaptive trials. And again, this all through simulation of these 1,000 dots. My type 1 error rate. For my adaptive trial, it's a little bit lower, 2.3 versus 2%. Now, if you're savvy at this point, you should go, you only simulated 1,000 trials, and that's not enough, and you are exactly correct. So ordinarily, I would do a lot more of these. The power of this trial has gone up, and 1,000, pretty close to getting enough for this. So 77% for the fixed and 82% for the adaptive. So I've gained power through this adaptive trial. Now, if you make a comment, Oliver, you got those 25 trials that actually picked the low dose and won. When you did the fixed trial, which I did the fixed trial, we didn't even ask that question. We just computed the power of the trial. This is one great thing we found about simulation. Going through those examples gives you a much better understanding of what kind of decisions you actually make at the end of the day. So, not just your type 1 errors, your type 2 errors, but your supposed type 3s, type 4s, everything else on, what kind of interpretation issues, what do I need to see out of this? So the simulations actually bring out that question, well, what if I won the trial but I picked the wrong dose? How often does that happen? This is often the kind of question that you only ask when you've done the simulations. And then the sample size, you can see the fixed trial had no sample size saving, so there's no futility. On the adaptive trial, if the drug doesn't work, we save half the study half the time, 63% of the time. That may not be fantastic, but it's a lot better than nothing. The other thing that we've done is, because we did this dose selection, we put more patients on the selected dose. The fixed trial had 72 subjects. This trial has 90, because at 3 months, we stopped one of the doses and we moved to the other ones. That's important for considerations like a safety database. You're going to have more patients on there. So you've gained across the board by doing this. All right, so in summary, the main point of adaptive trials is to allow you to use the accumulating information in your trial to the trial. You're not changing the design. The design says to make changes to the trial. So what's happening here, you're allowed to make adjustments, and you have to pre-specify these, write these in your protocol, but it allows you to use that information, essentially driving with your eyes open. So this is avoiding inefficiency due to your uncertainty when the trial started. If you don't know in advance, a lot of times, well, if I'm going to know halfway through the trial, I might as well use that information halfway through the trial. Keep in mind, there are no formulas for this, so you have to do these kind of simulation studies. They can be involved. You have to spend like 16 hours a day with Christine telling you, get your simulations done in the other room. But anyway, it requires effort, so keep that in mind. There's more prep time, there's more, and this notion of in your first trial, this may not be what you want to do, but once you have the trains running on time, so to speak, this is something that can make the trains go that much faster and more smoothly. And certainly the simulations also can inspire you to ask different kinds of questions, and that can make for an even better trial. So thank you all very much. Yes?
Thanks, that's really interesting. My concern would be that if I'm completing my estimate for effect size, I don't know what it is. And so the other thing is setting your threshold for like your 300 ohm for like utility at 8.25. So do you have ways of interfacing with your model where I can live change my input parameters for my effect size and also for my fertility estimates to see how that affects the outputs for my making a decision?
So let me start with the first part. So if you don't know your effect size in advance, typically what we would do, I just simulated a couple things here. So I simulated 0, 0 for the drug, and I simulated 1, 3. In practice, what we would do is we would simulate over a broad range. So if you say you don't know the effect, maybe it's 1, 1, maybe it's 1, 3, maybe it's 1, 5, maybe it's 3, 5. We would simulate every single one of those. And what we would end up doing is we would show you, here are the results with every one of these particular scenarios. You will run into the situation that some choices on when to do the interim analyses are good for some treatment effects and bad for others. What you want to do is find, there's usually a set, I'll say usually, so there's usually a set of design choices where you have reasonably good behavior over that entire range. So we would try to find a setting where, okay, nothing goes off the rails, so to speak. And we would look at all of those, and it becomes a conscious decision on your part. If you really can't find optimal behavior over the entire range, then you'll have to make a choice. But usually it's a far less stark choice than not being adaptive at all. If you're not adaptive at all, you're stuck with, hey, this fixed trial works great here and horrible here, and the other fixed trial works great here and horrible there. You try to find something, and it's always going to be the situation, hey, this works great here and good everywhere else is what the aim of this.
And then why did you set the p-value threshold at 0.25? Is that just
Pure arbitrariness to make things simple. We would play with a lot of different rules. And as a Bayesian, mine would all be in terms of posterior probabilities and things like that as well. But no, that was entirely simplistic.
Kurt, it also is a little bit right about sort of one tail versus two tail.
Yeah, that's part of it. I mean, so we would, one of our favorite rules, for example, is to try to predict the trial forward. So at 3 months, you can make what we call a predictive probability, where we say, if you continue this trial, what are the odds that you're going to win?
Yeah.
And that's more of a decision utility kind of idea. If that probability is only 10%, why am I enrolling the rest of the trial when I have a small chance of winning? If that probability is 50%, then maybe it's worth it. And it depends on the setting. If I had an Alzheimer's drug and I had a 10% chance of trial success, that changes everything. So I may go forward with a 10%. If this is a Me Too drug where this is non-inferiority to 5 other drugs on the market, I'm going to need a little more than that in order to be worth the resources.
Two questions are asking the cost and also the recruitment. If you have this slow versus fast progression, that you will like example versus say slower progression, ELS, for example, is there an advantage in terms of duration of the trial in one versus the other? The second is you want to recruitment advantages or challenges.
So I'm going to defer the recruitment to Will, so that's going to come to you in a second, so be ready. So for the key components of whether an adaptive design is helpful or not is the ratio of time to information to the accrual rate. So if you're accruing, we had a weight loss study, for example. They come in, they only want to do an adaptive design, and we want to do this and that and the other thing. We ask them, so how fast are you going to accrue? Well, it's a 1,000-patient trial. Well, it's a 6-month endpoint, and we could accrue the trial in the first week. Okay, there's not much I can do to help you there. So, because the whole thing's in, by the time you know anything, your accrual's all done, everything that I could possibly help you with, the timing doesn't work out. If you're accruing slowly, then this is one reason they're very useful in rare diseases, for example, where, okay, I'm accruing 1 patient every month or something like that, and then you've got a lot of time. Time to information is the second part of your question. Time to information is really important. So if you're talking about a 2-year endpoint, for example, then I get to these interim analyses, I've got lots of incomplete patients. So it depends on how much you actually can predict from these. If you have biomarkers or you have earlier endpoints that are decently predictive, you can adapt on those. So for example, we do a lot of device trials. They have 2-year endpoints. If I know how the patients are doing in 6 months, I've got a pretty good idea on how they're going to do in 2 years. I don't know, I do know some things about ALS, but not enough to comment on exactly what's the right time to do it. But if you're talking about a long endpoint, you usually would adapt on biomarkers. And you'd have to account in the simulations, are the biomarkers highly predictive or weakly predictive? And you may not know that in advance. And again, you want the trial to work under both circumstances. I don't think you've lost anything with the adaptive trial other than the time to plan it. But it doesn't require a bigger sample size or anything horrible like that. Will,
I don't want to be like a politician and perhaps answer the question I was hoping you would ask as opposed to the question you asked. So let me just make sure I have it straight. Are you thinking of, is it the question as to what degree could a design feature that sort of potentially has the patient's back to an extent of giving them a greater probability of getting something that's good could be used as a recruitment tool? Or, I don't want to make this sound dirty, but do you think, would it change people's likelihood to recruit or to consent to the trial? Is that?
That's probably where I might be.
Oh, okay. So the answer to that is I don't think we know well.
There's one paper that says
There's one
people are more willing to participate in a trial where they're told that there's a greater likelihood they'll get a working drug.
Can you say that in a consent form, like legally, like that's fair, that's technically okay to say?
Well, so okay, let me just give the example Josh is talking about, because some of the, we could have an entire 4-day conference on this subject, and we could have biostatisticians and ethicists in fist fights about this. There was a study I did. So as an academic, sometimes you have medical students who want to work with you. And when you have medical students who want to work with you, you want to keep them busy. Because the more you keep them busy, like when I was a medical student at the University of Cincinnati, one day I was learning how to suture, and this dude sliced off the tip of his finger, and they said, go put that back on, right? It can be occupied for 2 hours. That was great, because then the faculty could actually see patients, teach the residents, do other things. So I had students who wanted to research with me. So I gave them this project where they went and surveyed something like 408 emergency department patients and gave them a hypothetical situation regarding an acute stroke trial. Because one of the things, I did a stroke fellowship in Ann Arbor, and then I was like, we're too healthy and wealthy here, there's just not enough strokes. So I had to basically simulate strokes by just asking the general public what they would do if they had a stroke, because we didn't have enough strokes. Because this was helpful for the medical students, because while I couldn't predict when strokes would occur in the emergency department at the University of Michigan, I could predict when people would happen at the University of Michigan Emergency Department, since we're always quite full. And I'm sorry if you've had a long wait at our or any other emergency department. So they presented, this is an experiment that you can actually go back and look at exactly how it occurred. It was published, Jason Ternice is the first author, it was published in the Stroke Journal. The actual videos we showed people are on YouTube. We showed them basically you have had a stroke, you suddenly cannot move the right side of your body. I didn't talk exactly like that, but so that these poor medical students had to show this to hundreds of people. They had to hear me say that hundreds of times. He still okay. He's actually went to emergency medicine residency, but and what we did is we explained 2 different trial designs. One was just a regular acute stroke trial, similar to the TPA. It's sort of patterned after the TPA study. We had a fake consent form, all this stuff, and we explained it to people one way, fixed trial. And then half the people, based on point flip, they didn't see both. They just saw one or the other. This wasn't a repeated measures within an individual. Half the people got one, half the people got the other. The other half, we gave them this idea that there was a design, which I would never use this design, because it used response adaptive randomization in a 2-arm state, and it actually was an adaptive design that would shift patients as the trial went on to the arm that was winning. So collectively, over the course of the whole trial, more people would get the better thing, which in this case could either be TPA or a special new drug, fake drug called XPA. So over the course of the trial, your likelihood would be getting better and better over the course of the trial of getting one of those drugs, if one of those drugs was better. So in terms of how the consent form would need to be structured, it would have to be it would have to have a couple aspects of this, and a lot of times we don't really mention this as a major selling point at all because it's very minor shifts. But because it was an experiment in terms of a survey, we actually made it so it could switch pretty heavily towards the better drug. And about 67% of people would consent to that dangerous acute stroke trial if the trial, quote unquote, had their back. And we defined a priori, as we were telling people about this, that the study was halfway recruited, so there was information. If you're the first person in that study, there's no benefit to there's no information, there's been no adaptation. And there's no loss, right? It's just like a regular study. Versus the people who got the regular study, about 54% of people consented into that study.
If you're going to get a disease, you should always get it later. That's always helpful.
And I deal in unpredictable sudden diseases like stroke and cardiac arrest, which are hard to delay. So that puts some sort of unique things in the situation. There are lots and lots and lots and lots and lots of issues. I would say that the bottom line is I wouldn't use an adaptive component necessarily as an inducement to have people do the trial. It's harder to explain. In an acute stroke trial setting where I have like 5 minutes to explain this, people didn't necessarily understand the design. So we did a follow-up study, I still need to resubmit to another journal, where we gave people better education about what the design was so that they actually understood it. We had the algorithm ask questions for understanding along the way. So that's a little lengthy, and I think we probably want to take a break. All right. So.
Can I ask one question? If you have investigators wants only 2 arms, there's no multiple doses, there are no different drugs. Is there anything to adapt on in those?
Well, that becomes complex. Generally speaking, in the current regulatory environment, you absolutely don't want to do adaptive randomization. You're down to futility of success stopping, and you're in the group sequentials, things like that.
The one reason, and there was an article that I published in JAMA. If the disease is terrible, and then there's like 50 patients in the world, there may be a compelling reason to put that in. Now, as you know, the most efficient way statistically to compare 2 groups on a binary endpoint is 2 equal-sized groups. So you are trading away statistical efficiency for potential improvement of the collective outcomes. If it is some terrible, untreatable disease, the clinician may say that there are reasons to do that. And Dr. Zhao at MUSC has looked at some of these trade-offs as well. He knows quite a bit about that too. And it's a very active area. There's no way to weight the utility necessarily that we know of what you're losing statistically versus what you may be gaining from a patient-oriented sort of potential benefit if more people are getting something that's sort of beneficial. But as Roger pointed out at the beginning, since the best group to be in most of the time is the placebo group, getting more people on placebo is potentially one of the findings of these things. And in most cases, if placebo is starting to win and your RAR is putting more people on placebo, the trial should be turning off. All right, take a break.